Let's start with this problem that Euler posed about walking around the city of Königsberg. The puzzle goes like this. You're supposed to walk around the city and try to visit or cross each of the bridges exactly once. So let me show you an attempt to do that. Let's say I start in landmass D and I cross this bridge over to C, over here to A. Well, I'm kind of stuck here. I can't get back to any of the other land masses without repeating a bridge. Okay, well, maybe I just didn't try hard enough. Let me maybe start in the middle this time. I'm going to visit up into A, then B, then C. Well, if I go back to A, I'm in trouble, and if I go down here, I'll never be able to cross that bridge to A. So that didn't work. And so you can try to solve this. Just try and do what you can do to cross all the bridges, and you'll quickly discover that it just can't be done. No matter what you do, you get stuck at a landmass before you've crossed all the bridges. So in order to make an abstract diagram of this problem, we collapse the landmasses into vertices of a graph, and the bridges are connections between those landmasses, so the bridges are edges. So if this dot down here represents landmass D, and the middle is B, the top is A, and the right is C, then there are two bridges from D to B, two from B to A, one from A to C, one from B to C, and one from D to C. So this graph is an abstraction of the city of Königsberg from the perspective of connections of land masses with bridges. And so there's something about this graph that makes it impossible to visit all of the bridges exactly once. And I don't know if it's apparent to you what the issue is here, but that's the type of thing that we're going to be studying in this section. So let me just take a look at this graph as a graph. I noticed something about the degrees of the vertices. The degrees of the vertices are as follows. The degree of D is 3, B is 5, A is 3, and C is 3. That's going to have some relevance when we talk about so-called Eulerian circuits, which is the type of walk that we're trying to make in this bridge problem. Okay, so let me start with some definitions then. Trails, paths, and walks. So these are all definitions of the type of thing that we were doing in Königsberg. We're walking around a graph, visiting vertices and crossing edges as we do so. So if you have a graph, then a walk from one vertex to another it's a walk. Well, it's a sequence of vertices and edges that you cross to visit them. So let me get an example graph going here, and I'll talk about all these different kinds of walks that we can make. Okay, so here's a graph G down here, and I'm going to write out some sequences of vertices and edges that represent all of these different kinds of walks or paths that we can make. So a walk from one vertex to another, let's say we're going to walk from V1 to V3 or something. And without any sort of restrictions on how many times you can visit the vertices or the edges, you just call it like a general walk from V1 to V3. So here's an example of a walk from V1 to V3. There's many. Okay, so to get like a visualization of that walk, you start at V1, you cross E1 to V2, then you go to V3 using the edge E2, then over to V2 using edge 2 again, and then back to V3 via edge 2. So you kind of start at V1, V2, V3, bounce back to V2 and V3 again. That's a perfectly good walk. Okay, now some other types of walks. You call a walk, well, yeah, you call a walk a trail if it starts at V and ends at W, but you don't repeat edges. Like you can see here, I repeated the edge E2 twice, right? So let me give you an example of a trail from V1 to V3. Okay, and let's get a visualization of this. I start at V1, I go over to V3 via edge 5, and then I go over to V4 via edge 3, whoops, and then I go over to V2 via edge E4, and then over to V3 via edge 2, like that. So that again went like this, over here, there, and to V3. So notice during that walk, I didn't repeat any edges, and you can see as it's written out, you've got edge 5, 3, 4, and 2. So none of them are repeated. So that's called a trail. Now a path is going to be a trail that does not contain a repeated vertex. So you don't repeat any edges and you don't repeat any vertices. So let's go from V1 to V3 in that manner. Okay, so you can see what this looks like. I start at V1, over to V2 via edge 1, V4 via edge 4, V3 via edge 3. So there's a walk from V1, or a trail from V1 to V3, not repeating any vertices, and not repeating any edges. Okay, where are we at now? A closed walk. So a closed walk is simply a walk that starts and ends at the same vertex. So I can take my original walk from V1 to V3 and walk back to V1 if I want. That would be a perfectly good closed walk. And I am not worrying yet about repeating any vertices and edges. In a closed walk, I simply start at one place and return back to it eventually. Okay, so here is a closed walk because it starts and ends at V1. Let's talk about a circuit now, and then a simple circuit. So a circuit is a closed walk, so it starts where it ends, and it doesn't contain any repeated edges. We're not going to consider circuits to be trivial, so a circuit needs to have at least one edge in it. But again, a circuit's a closed walk that doesn't repeat any edges. So let's just make a circuit from V1 back to V1. Okay, here, so this is a closed walk starting and ending at V1, but unlike the previous closed walk, this does not repeat any edges or vertices, well, edges, and yeah, so there you go, that's a circuit. I was getting ahead of myself. The simple circuits do not repeat any edges, and they do not repeat any vertices either. So actually, the one that I've just written is also a simple circuit. The only vertex that's repeated is V1, but that's allowed because that's the starting and the ending. So this circuit right here is not only a regular old closed walk with no repeated edges, but you also are not repeating any vertices. I kind of feel like I should give an example of a circuit that's not a simple circuit. Let's see if we can find one of those. So I don't want to repeat edges, but I can repeat vertices. Okay, I think that I found one. Here, if we start at V1 and go over to V3, and then go to V2, and then go to V4, and then back to V3, so I'm repeating vertex V3, then over to V5, and back to V1. I've not repeated any edges, but I have repeated the vertex V3. So that would be a circuit that, it's a perfectly good circuit, but it's not simple. So we're going to be interested in whether or not these types of paths and walks and circuits and things actually exist for a given graph, and the notion of connectedness is going to be important. So if you take a look at the graph that we were studying, it came in two big chunks, right? There was this chunk that I was walking around, and then there was this other isolated chunk over here with the vertex 7 and 6 that I really couldn't get to from where I kept starting at V1. And so since there are no edges between these two chunks, there's no way to walk in between them, basically. So if we want to introduce some vocabulary to talk about this notion of connectedness. We call two vertices connected if you can get from one to another by a sequence of edges. So like V1 is connected to any of V2 through V5, and V6 is connected to V7, but there are no connections between 1 through 5 and 6 and 7. And the graph itself can be called connected if every pair of vertices is connected. So a connected graph looks something like this. This would be a connected graph because you can go from any vertex to another graph, whereas the original graph we were studying is not connected because there's no path, for example, from V1 to V6. Now, if you have a disconnected graph, well, even a connected graph, you may want to reference the components. So like the original graph we were looking at had two big connected chunks. So a connected component of a graph is a graph. It's a subgraph, actually. It's connected, and it's maximal with respect to that. So let me clarify about that. Like, I could, for example, define a subgraph of G just to consist of vertex 6, right? It's a perfectly good subgraph. It's a subgraph of G. It's a connected graph in its own right, but it's not really maximal, so I don't call it a component of G. So the point is, H itself is not maximal in the sense that I could add on to V6 the vertex V7 and create a bigger subgraph to G that is also connected, and there's no other connected subgraph of G that properly contains J. So H is not a connected component of G, but J is. J is V6 together with V7. That would be a connected component of G. And it's very visual. Like if you look at G, you obviously see two connected components. This big blob here, and then this one here.